scale formation can happen in many other systems, including this membrane distillation. And anyway, scale formation, we are talking about several different inorganic salts that result in the scale formation, including calcium carbonate, calcium sulfate, and silica, and barium sulfate, strontium sulfate. There are many different types of the salts that can cause scale formation. Of course, calcium sulfate has been studied widely because it's very common and it's relatively difficult to control because its solubility is pH independent, unlike this calcium carbonate. Anyway, scale formation causes a lot of problems in reverse osmosis and nanofiltration membranes, and as well as the thermal desalination, such as MSF and MED, and of course MD. And sometimes we can even see some of the scale formation in electrodialysis. And once it happens, it is very difficult to remove, and it's also very difficult to clean the membrane. And it may also damage the membranes. So that's why people are very worried about the scale formation problems in the membrane systems. Membrane distillation has been recently studied also widely. And as you know, this is a thermally driven process, and it uses the hydrophobic porous membranes, and it has a lot of advantages like very high rejection and ability to concentrate the high salinity feed water, and also it can be easily combined with the renewable energies. So that's why many people are studying the membrane distillation. Of course, membrane distillation has several disadvantages, such as wettings and fouling and the energy issues. And when you talk about the fouling of the membrane distillation, we needed to consider the scale formation because this is one of the frequent type of the fouling that you can find in the membrane distillation system. In fact, I started my research on membrane distillation in year 2010, and my first paper published in year 2000 on membrane distillation was published in 2013. And in the meantime, I have been published more than 50 papers on membrane distillation. So in my presentation today, I'll just show some of the snapshot of my previous works on this topic. So let's talk about the scale formation in membrane distillation. This is an inherent problem because when we consider membrane distillation, we needed to treat the feed solution with high salinity. So that kind of feed solution has very high potential of the scale formation. So that's why scale formation is very common in many membrane distillation systems. And there is no single solution for taking care of the scale formation in membrane distillation. Some people say pre-treatment is effective. Some people say it should be cleaned. There are many different approaches, but in my opinion, all these kind of approaches should be combined to provide the solutions. Otherwise, we'll end up with a lot of problems resulting from the scale formation. Fortunately, we have a lot of experience from other processes like reverse osmosis and heat exchangers. And although membrane distillation itself is an emerging process, but as for the scale formation, we have a lot of similarities in the problems in MD with some other systems. So we can learn those things from other systems, and we can apply that so that we can have some ideas to take care of the MD scale formation. Let's start with the fundamentals of the scale formation. There are three steps involved in the scale formation. The first step is the induction time. In this period, nothing seems to happen, but this time is required, otherwise scale formation may not start. So this is some time for preparing the scale formation. And then nucleation happens, and the nucleation is followed by the crystal growth. So the nuclei created from the nucleation process start to grow, and then eventually we can see some of the scales in the solution or on the surface of the membranes. In fact, there are two different mechanisms of the crystallization happening in membrane systems. The first one is the so-called the bulk or homogeneous crystallization. And the second one is the surface or heterogeneous crystallization. In the first case, the nucleation happens without the help of the foreign particles or foreign surfaces. So it purely happens from the supersaturated solution. That's the homogeneous crystallization. On the other hand, in the case of heterogeneous crystallization, foreign particles or surfaces can act as a nuclei so that it can induce the crystallization. According to those different the crystallization mechanisms, in fact, there are two different pathways of the scale formation in membrane systems. The first one is the cake formation. The second one is the surface blocking. Cake formation happens as a result of the homogeneous crystallization, while surface blocking happens as a result of the heterogeneous crystallization. If you look at this slide, you can understand the situation more clearly. In fact, as I already mentioned, there are two pathways. If we go through the homogeneous crystallization pathway, supersaturated solution creates nuclei, and its size increases due to the crystal growth. And once it forms particles, they may deposit or they may be back transported, and the deposited particles will form the cake layer on the membrane surface. And that's the fouling mechanism. The second pathway is the heterogeneous nucleation, and in that case, membrane surface acts as a nuclei, so the crystal growth happens directly from the membrane surface, and eventually the surface crystal cover the membrane surface, and the membrane becomes impermeable so that the plastic line happens. So these are two mechanisms of this scale formation. One thing that I have to mention is, even if we use the same membrane and even if we use the same feed solution, depending on the operating conditions, sometimes homogeneous crystallization predominantly happens. Sometimes heterogeneous crystallization predominantly happens. So that's kind of the things that we needed to understand, because sometimes they happen at the same time, and then sometimes one of the mechanisms are predominant. So depending on those mechanisms, the fouling patterns changes. So I previously mentioned that there are three parts in my presentation, and the first part is the analysis of the scale formation. And there are three steps that we can analyze the scale formation. The first step is the one that we predict the scale formation prior to the actual MD operation. In that case, we can develop and apply the theoretical model, or we can use computational fluid dynamics to simulate the hydrodynamic conditions. And based on that, we can also just predict the fouling patterns. During the MD operation, we can just see the changes in flux with time or concentration factor. But recently, people have applied the new technique, so-called the optical coherence tomography, which let us monitor the progress of membrane fouling during this membrane operation without destructing the membrane module. After the membrane operation, the way that we can see the scale analysis is, of course, autopsy. So I'll show you some of the pictures and some results from my previous papers or some of the works that I'm currently working on. And as for the theoretical models, I have been developed and applied three different types of the model. The first one is the mathematical model that considered two different crystallization mechanisms, and by solving these the equations, we can just predict the flux decline as a function of time or concentration factor. Sometimes this simple model may not be really accurate, so in that case, we apply the ANN or some other techniques to statistically predict the scale formation and membrane fouling. Recently, we are working on a new approach, so-called the system dynamics model. And in that case, we can just have some relationship between different sub-processes. And with that, we can have a dynamic simulation as well as the Monte Carlo simulation that allow us to consider the uncertainty of the process. So this is one of the new approach that we are currently working on. CFD is another techniques that let us directly simulate the hydrodynamics, and based on that, we can have more accurate information on the scale formation process, the process and the fouling phenomena. In one of my previous research, we used the lab scale membrane modules, and we developed the geometry based on this module. And this is a 3D CFD, and by doing that, we can accurately predict the flux decline with the time by using this model. CFD can be also applied for understanding what's going on inside the module. So in the right side picture, we have a CFD simulation, and we analyze the point where the flow velocity is decreasing or increasing, and based on that, we see where the scale formation can happen more actively and where the scale formation may not happen actively. So that kind of analysis can be done by carrying out this kind of CFD simulation. OCT is a new technique, and this is one of the examples that allow us to see what's going on during this membrane of MD operation. So in this case, we use the OCT device, and we monitor the membrane modules. And before the experiments, we see that the membrane is very clean. And when the flux decline is not happening, so in the middle of the process where the flux is still very high, in that case, we only see a couple of tiny scales on the membrane surface. And after having flux decline due to the scale formation, as you can see that there are lots of crystals covering the membrane surface, thereby decreasing the flux through the membrane. So this is a simple example, but this technique can be applied to see the exact point where we need to start the cleaning or flossing or some other actions, because we cannot just determine that kind of times based on the flux information. Autopsy is the final tool for the analysis of the scale formation. So this is one of the examples from my previous works. And in that case, we use the full-scale hollow fiber MD module. And after the experiment, we took these fibers and we just classified the fibers in different positions, and we carry out several analysis, including SAM, EDS, FTIL, no, FT, this is AFM and XLD, and some other analysis was also done, which let us have understand what has happened inside the membrane module. So this is like a destructive method, but it can provide a lot of useful information. So let's talk about the second part, which is about the module. And when we talk about the membrane distillation modules, there are two types. One of them is flat sheet or spiral rounds. The flat sheet also includes the spiral rounds membrane modules. And the other type is hollow fiber. And as you know that those modules have pros and cons, and but when you talk about the issues related to the scale formation, in the case of flat sheet membranes, we needed to consider whether this module has the spacers or just the flat flow channels. And depending on that kind of situation, we needed to apply different techniques. And in the case of hollow fiber, there are two ways for running these the modules. The first one is inside out, and the second one is outside in. And we needed to be careful when the feed solution has some possibility of scale formation. I'll actually tell you about that a little bit later here. So the first one, when we use the flat sheet membrane modules, sometimes we can put some spacers or we can have some baffles, and based on those shapes, we can either retard the scale formation or accelerate the scale formation. So in this study, this is also one of my previous works, we just designed the baffles to alter the flow patterns inside the plate and frame membrane modules, and we compared that, and we found an interesting result that by changing the baffles and by changing the shape and the numbers of baffles, we sometimes can increase the flux, and which is actually better than the membrane modules without any baffles. So that actually shows some potential for us to control the scale formation by having a proper baffle inside the membrane module. This one, we compared the inside-out hollow fiber membranes and outside-in hollow fiber membranes, and although the pure water flux were similar, when we treat the feed water containing scale-forming ions, outside-in was okay, but inside-out was not good. And the reason is, in fact, in the case of inside-out, in fact, the flow velocity inside the fiber is actually higher than that of the module of outside in. However, since the channel inlet of the fiber can be blocked by the crystals generated through the homogeneous crystallization, block decline happens rapidly, and that's actually the problem why we should not use inside the out hollow fiber membranes for when scale formation can happen. So the third part is about the strategies for scale control, and there are many different strategies in each steps. So if you just imagine the steps for the scale formation, initially, we start with the supersaturated solution, and nucleation and the crystal growth happens. And once the crystallization happens, it may deposit it may form the cake layer, or it may form the surface crystals, and so the flux decline happens. And after that, what we can do is the um, cleaning of the membranes. So in each case, for taking care of the supersaturation, we may dilute the feed solution, or we may use the NF membranes to separate the divalent ions. Although they have some potential, but I'm not going to talk about that parts because that's not the problem of membrane distillation. And if we wanted to retard the nucleation or crystal growth, we can use antiscalant, and I'll just show you some of the results related to the antiscalant addition. And to prevent the deposition of bulk crystals, we can increase the flow rate, or we can alter the hydrodynamic conditions to prevent the to enhance the particle back transport, or we can remove the crystal particles inside the system. And as for the surface crystal, we can also alter the hydrodynamic condition to control concentration polarization or temperature polarization. And cleaning, we have several options for cleaning the membranes. So in each case, since I use too much time, so I'll briefly mention about some of the results in each case. As for the pre-treatment, we have applied several new pre-treatment, and in the case of wastewater treatment using membrane distillation membranes, and when scale formation happens, we use the micro bubble treatment combined with the special filtration system, and we were able to prevent the flux decline very successfully. So this is one of the success story of the pre-treatment. As for the antiscalant, we compared several different antiscalant, and they are designed for reverse osmosis application or the MSF application, but there is no antiscalant for membrane distillation. Anyway, we compared that, and we found that some antiscalant is very good, some antiscalant is not really effective, and we just try to correlate the chemical structures and the antiscalant effect. And in order to control the cake formation or surface crystallization, we needed to increase the flow velocity or shear rate near the membrane surface. And one of the technique for doing this is the aeration. So we designed the aeration system to put the air inside the membrane module, as you can see. And of course, as you can easily imagine, aeration is effective to retard the scale formation. We cannot completely prevent the scale formation and flux decline, but it can just retard the scale formation a little bit.
Professor Lee, we need a little bit hurry.
Okay.
Yeah.
Okay.
Yeah.
I'll quickly go through this.
Yeah.
And this is the one that we use the inline filter. Since the crystal particles are problematic, we can just remove them continuously using a filter inside the recirculation loop, and that was very successful. Temperature reversal is an interesting idea because in the pressure-driven membrane systems, we can reverse the driving force to reverse the flow direction, and that's the backwashing. And we consider the similar concept by reversing the temperature gradient, and that was partly successful. Another one that we are currently working on is the membrane vibration. And yesterday, one of my students presented the result related to this one. And what we are looking at is the special patterns that can maximize the scale control of the scale formation problems. And when the membrane is completely fouled, we needed to clean the membrane. And of course, the ultrasound can be considered, and we explored the different operating conditions, and we found optimum condition that can successfully clean the membrane and that does not damage the membrane. Okay, so that's the last slide. As I already told you, that scale formation, we first needed to understand the mechanisms, and we have to understand that there are two pathways, and depending on the mechanisms, we needed to have different solutions for taking care of those problems. And the analysis of scale formation is important because based on this information, we can take care of the problem. And we also needed to work more on the design and optimization of membrane modules, because if we can successfully retard the scale formation problems in the module, we can significantly reduce the effort for controlling the scale formation outside of the membrane module. The final one, I have just quickly introduced several options for controlling the scale formation, and we needed to optimize the conditions, and we also needed to optimize the combination of those techniques. And that's all of my presentation. Thank you very much for your attention.
Thank you very much, Professor. And we have a second speaker ready. That's the reason why I was.
Okay, sorry.
So if you don't mind, everybody has a lot of questions, and then please leave the chat box, and then Professor Samoli will reply by text, and then we can go to the next speaker. Is it okay, Professor Lee?
Yes, of course.
Yes.
Sorry about
that's all right. So you can
taking too much time.
Yeah, you can chair the second person. I will check the last one.
You can continue to have the second one.
All right. We have a next speaker from the Nanjing Tech University, Yang Mao. She will talk about hydrophobic graphene-based membrane for MEMDES desalination. So please, go ahead when you are ready.
Okay. Thanks for the chair's introduction. And can you look at my thing?
Yes.
Yes.
Yes. Can you listen my song, my voice?
Yes, I can. Can you make
okay.
presentation? Yeah, full screen.
Okay. Thank you.
Right.
Now begin my presentation. Good afternoon, everyone. My name is Yang Mao, and I come from Nanjing Tech University. It's a great honor for me to present my work here. The topic of my presentation is hydrophobic graphene-based memories for memory distillation. And my supervisors are Professor Wan Qingjing and Professor Gongping Liu. The outline of my presentation includes these 4 parts. As we all know, memory distillation, namely MEMDES, is a process that combining memory separation and the distillation process. The driving force of it is the temperature difference of both sides of the membrane and the vapor transport through the porous and hydrophobic membrane. And the memory distillation can be operated in at atmospheric pressure, and the theoretical rejection rate of this process is about 100%. And we can also use this technique to treat the concentrated brine. And we often classify this technology into 4 kinds: DCMD, AGMD, STMD, and VMD. In my work, I mainly studied DCMD and VMD. And concluded from the formal reported literature works, main challenges in developing this kind of technology mainly include these 4 parts. The first is how to keep the stability of the membrane's hydrophobicity. And the second is how to improve the low permeant flux. And thirdly is how to prevent the surface wetting. And the most important is to develop new materials for memory distillation process. Among new materials, graphene or graphene oxide has showed unique materials advantages. The first is that the bond energy between water molecules is larger than the adsorption energy of the water molecules on graphene surface, so it shows the intrinsic hydrophobicity. The secondly is that the nanochannels of graphene-based membranes will limit the passage of macromolecular contaminants, and it showed anti-pollution properties. The third one is that the fast radial heat transfer rate of graphene and the easy modification of graphene oxide also make it suitable for memory distillation process. And the people often fabricate graphene-based hydrophobic memories by these four methods, such as CVD method, deep coating, crippling or unfolding, and the chemical graft. Now, typical works about graphene-based memories for memory distillation mainly include these two parts. The first part is to fabricate graphene-based mixed metric memories. And the graphene is often used to improve the surface roughness, the hydrophobicity of the memory, a larger diffusion area for vapor transport, and also can be used to improve the thermal stability or mechanical stability of the memories. The second typical work is graphene-based pure memory by CVD methods. CVD methods can provide high-density nanochannel of graphene memory. And also, this kind of memory will show strong antifouling ability for mineral oil or surfactants. However, the most important thing for this kind of memory is that it will need high cost and it is difficult to control the course of the memory. So for us, it's important to develop a simple method to fabricate pure graphene-based memory. So in my work, my research idea is that I chose the nanoparticles to integrate graphene oxide to improve the porosity of the memory, and chose a hydrophobic modification modification to improve the hydrophobicity of the memory. Concretely, look at the diagram. I chose nanoparticles silicon dioxide to integrate the graphene oxide to form the porous structure, and then we treated this porous structure with HDTMS solution to finally obtain the optimal hydrophobic and porous graphene-based memories. And finally, we utilized this kind of memory for vacuum memory distillation. Firstly, we performed the SEM and FM of our materials. We found that the GO nanosheets, we utilized that with the lateral size of about 1 to 2 micrometers and laminar thickness of about 1.8 nanometer. And the nanoparticles we used in this work was with diameter of about 3 to 500 nanometer. And then is the cross-section SEM figures of different memories with different mass fraction of nanoparticles. We could easily find that the nanoparticles are evenly loaded on the interlayer to form the porous memory with different mass fraction of nanoparticles. And continuously, SEM and surface water contact angle of these different memories were characterized. We find that with the nanoparticles mass fraction increased, the water contact angle, namely hydrophobicity of the memory surface, was increased. However, when we introduced excessive nanoparticles, local agglomeration will happen. AFM character results also demonstrate with the increase of nanoparticles, the surface roughness will be increased. So concluded by these results, we found that the hydrophobicity of our memory mainly resulted from both of the enhanced surface roughness and the hydrophobic modification methods. STS and FDIR results also demonstrated that in this work, HDTMS has been modified into GO and nanoparticles by hydrogen bond and covalent bond. Then is the first investigation about the effect of different treatment temperature on our surface hydrophobicity and VMD denomination performance. We could easily find that from the left picture, we find that the silicon dioxide graphene oxide HDTMS memories shows the highest hydrophobicity. And we analyzed that it is the results of signaling of roughness and chemical modification. Also, this kind of memory only just demonstrate hydrophobic property only when we annealed the memory equal or larger than 80 centigrade. And however, when we annealed the memory at about 100 centidegree or 120 centidegree, the thermal reduction of graphene itself will result in the low flux of the final memories. So finally, we chose the optimal temperature of 80 centidegree. And then firstly, we investigated the VMD designation of memories with different nanoparticles mass fraction. And we could find that the optimal mass fraction of nanoparticles is about 15%. When we added less nanoparticles, it cannot provide enough porosity. And however, when we introduced excessive nanoparticles, it will also cause a decrease in water flux due to the local agglomeration occurred. Then continuously, the VMD designation of our optimal memories under different feeder conditions was also performed. We found that the water flux was increased with the feed temperature increase. And when we changed the salt concentration of the feed, the water flux ranged little. In order to analyze that phenomena, we have formed a theoretical analysis of these memories under different feed conditions. We found that the vapor pressure was increased with rising the feed temperature, and that will contribute to a larger driving force, and thus with higher total flux. And however, the water vapor pressure varies little within the studied salt concentration, and it will lead to the water flux just showed little difference. The most important part of this work is that we also investigated the antifouling properties of our graphene-based memories. We found that the hydrophobicity and the desalination performance remains relatively stable, even though we have added model foulant such as SDS and HA in the feed. However, it needs to be mentioned is that the weak pi-pi interaction between the foulant HA and the GO will result in a slight decrease in the vapor flux. Continuous operation stability of our graphene-based memory was also investigated in this work, which about 117 hours. And by continuous changes the feed, the water flux maintained within 7 to 9 kilograms per square meter per hour. However, in this work, the salt crystals falling problem in our membrane surface cannot be ignored. For further exploration, in our previous work, we have chosen the nanoparticles to integrate the gel nanosheets. However, how about we use in situ synthesis instead of physical mixing, and use porous nanoparticles instead of non-porous nanoparticles? And will this method will lead to a larger or higher water permeable flux? So in our recent work, we have in situ synthesis of these porous nanoparticles in gel followed with the same HDTMS modification methods. We could find the water contact angle of our membranes is about 130.7 degree. And the nanoparticles with size of about 15 nanometer. And finally, we tested the DCMD performance of this kind of graphene-based memories. It showed higher water vapor flux with about 16.8 kilograms per square meter per hour. And this work is ongoing, and we find that this strategy showed better separation performance. And that's all my concrete work. We have got the several conclusions. We have proposed new types of hydrophobic and porous graphene-based memories, and the hydrophobicity and the porosity of graphene oxide memories could be improved, and the continuous stability of our membranes was fully discussed. And in our future work, we will continue to construct new architecture by taking full advantages of graphene itself's advantages, such as the intrinsic hydrophobicity of graphene and the isotropic heat conduction of graphene materials. And that's all my presentation. Thanks a lot for the conference team to give me the opportunity to present my work here. Thanks a lot. That's all.
All right, thank you, Yang Mao. So we have one question for Yang Mao. Anybody just to put any question to her? No?
Thanks the question. I have seen the question.
Mm-hmm.
How is the scaling situation?
Yeah.
About scaling situation of our graphene-based memory, we now haven't do some investigation about that. We in our recent work we have also concentrated on how to improve the separation performance of graphene itself, and we have do some work about how to prevent this kind of scaling, such as some flow rate, such as FAS, to modify it with graphene oxide to improve the anti-fouling or anti-scaling of our graphene-based memories. Concrete scaling situation of this kind of memory haven't been investigated.
Okay, we have another question.
But some work have been performed to prevent this kind of phenomena.
Okay, thank you, Yang Mao. From Fei Guo, did you observe any cracks or flaws during the preparation process of a geoparticle membrane?
Sorry.
So,
Could you control the scale by
okay, in the chat box.
chat?
Yeah.
Cracks or flaws during the preparation of about this question, as we all know, for membrane distillation materials, the porosity or hydrophobicity is the most important thing for this separation process. And some cracks on our graphene surface or cross section, we think if these cracks is not very large or big, it will not affect our separation performance. However, if these cracks was large enough, it will destroy our affect our separation performance.
All right. So, okay, thank you for your wonderful presentation, Yang Mao. So we will close your talk now, and then we have a last speaker. And
yes, I'll introduce the last speaker.
Yes,
and
please.
the last speaker is Ms. Jing Zi, and she's from Chinese Academy of Science. And in fact, I met Dr. Zheng Li in Saudi Arabia, so I feel like this world is very small. So anyway, she brought a very interesting topic about the recovery of low concentration ethanol from wastewater produced in traditional Chinese medicine industries by evaporation. So it's not membrane distillation, but it is related. So please, Ms. G, please share your result with us. Please go ahead.
Thank you for the introduction, Chair. And I have sent the pre-recording video to
Yes.
the conference. So.
Dr. Yang Mao, could you please stop sharing your screen so that we can play the pre-recording for the next talk?
Yang Mao.
Yang Mao.
Okay, I can. Okay, I can share. Okay.
Yeah, perfect. Yeah, I'll start the pre-recording. Just give me a second. Is it visible now?
Good afternoon, everyone. My name is Jinji, and today my presentation is about the recovery of low-concentration ethanol from wastewater produced in traditional Chinese medicine industries by evaporation. And this is the outline of my presentation. I will first introduce the background of my project, and then the methodology, followed by some preliminary results and discussion. And the final part is a conclusion and future work. First is the background of this project. Traditional Chinese medicine, TCM, is one of the national quintessence of our country. It is the material basis for medical development in China. TCM has also played an important role in the prevention and treatment of COVID-19 during the pandemic. Generally, most of the TCM recipes or formulas are produced by the alcohol precipitation method to achieve good purification level, improve the product quality, and ensure the clinical healing effect. As shown in this flowchart, the overall manufacturing process of TCM products includes multiple steps, and it is actually struggling to meet the requirements of environmental friendly and sustainable production. That is mainly due to the significant amount of wastewater produced in the process. Researchers have shown that when total TCM product output exceeds 1,000 tons, then every ton of final TCM product means 130 tons of wastewater will be generated at the same time. And the wastewater actually contains a significant amount of ethanol, because ethanol is a general solvent, always a precipitant, used in the extraction of TCM. The large consumption of the fresh ethanol also results in the high cost of the process, especially if it's not reused. And because ethanol is highly flammable, the storage of ethanol is actually another potential safety risk. Therefore, the efficient recovery of ethanol is crucial for the development of modern TCM production. Currently, there are several separation techniques can be used to recycle ethanol from the TCM wastewater, including distillation, evaporation, membrane distillation, reverse osmosis, adsorption, and etc. Evaporation has been regarded as one suitable choice due to its non-toxic nature and simple mechanism. As shown in this figure, the PV process is just driven by the partial pressure difference and concentration difference. The desired component could pass through the membrane based on the selective dissolution and diffusion mechanism in the vaporizing process. And as mentioned before, and also we all know that distillation column is one of the most commonly used technology to recycle ethanol from, especially when ethanol concentration is significantly high. As shown in this flow diagram, normally in the TCM manufacturing factory plant, the wastewater discharged from the production line will be first treated by the distillation column, and when the concentration of the vaporized ethanol is greater than 92%, it will be then transferred into an ethanol storage tank for subsequent use. On the other hand, when the ethanol concentration at the bottom of the distillation column falls below 30%, it's just discharged directly. But actually in this case, we can feed the bottom solution to the evaporation system for further recycling treatment. So in this work, a bench-scale evaporation setup was applied and a specific membrane module was designed. So during the PV test, the TCM wastewater will be kept at certain temperature and then pumped through the membrane module and then go back to the reservoir. And inside the module, the mixture solution will be forced to travel all the way through this long and curvy channel and in constant contact with the membrane pressed on top. This curvy mesh-like channel design is to maximize the contact area and contact time between the membrane and the feed solution. The vaporized ethanol will then permeate through the membrane under vacuum and condensate in the cold trap, and this buffer bottle is just to protect the vacuum pump. The whole experimental cycle will last for 6 hours, and the permit in the cold trap will be collected every 1.5 hours. The ethanol concentration in the feed, retentate, and the permit will be determined using gas chromatography. In our preliminary study, we have prepared some PV membranes by simply coating a layer of PDMS on the support material by casting and then followed by curing and solvent evaporation. The PDMS we used was Silgard 184 and solvent was isooctane. So the supporting material was PAN ultrafiltration membranes. PDMS dope solutions with 2 different concentrations have been used to prepare the PV membranes. So we first studied the effect of PDMS concentration on the ethanol recovery efficiency of the prepared membranes. Because the project is still in the initial phase and is given limited time, so we just use ethanol water mixture solution instead of real TCM wastewater to carry out the experiment. The initial alcohol concentration in the feed solution was fixed at 157.86 gram per liter, and the table on the top summarized the experimental conditions of the PV test. The table at the bottom indicates the flux of the 2 membranes, and the figure shows the concentration change. It can be observed that the membrane made by 30% PDMS concentration have very obviously higher selectivity with a slightly lower flux. This is because the higher PDMS concentration made the membrane surface more hydrophobic. So in this case, even if some water molecules are also vaporized due to the high temperature, it is still hard for them to penetrate into the membrane and pass through going to the permit site. So based on these results, we decided to use 30% PDMS membranes in all the following experiments. Apart from the PDMS concentration, we also investigated the effect of casting thickness on the ethanol recovery for different membranes. As shown in this table, if we compare the ethanol concentration change of the 20 micron thick and 40 micron thick membranes, it could be found that the membrane with larger thickness shows better ethanol selectivity, and this is probably due to the increased membrane resistance for water molecules to diffuse through the membrane, especially the coating layer. However, if we increase the membrane thickness further to 60 micron, then the membrane selectivity for ethanol disappeared, which was quite unexpected. And we guess this may be attributed to the significant high diffusion resistance due to the ultra-thick coating layer. So in this case, both ethanol and water molecules were impeded by the coating layer itself. Another possible reason is that our self-made membranes may have some defects or pinholes, which will also reduce the membrane selectivity. Further experiments will be conducted to explore the exact reasons behind this unusual phenomenon. Apart from the membrane itself, we also studied the effect of the experimental conditions on the ethanol recovery efficiency. But unfortunately, we only have time to run the PV test at 2 different temperatures that is 60 and 70 degrees Celsius. And here the memory flux is decreased a long time despite of the feed temperature. But obviously, higher feed temperature leads to larger flux. And it's also noticed that increasing the feed temperature could increase the ethanol concentration in the permit as well, as shown in this bar chart. And this could be attributed to two reasons. One is the mass transfer coefficient of the molecules, and the other is the absorption of molecules into the membrane. According to the literature, the effect of increasing temperature is positive on diffusion but negative on absorption. When the feed temperature goes higher, then the free volume in the membrane will increase, so the diffusion rate of the molecules through the membrane will also increase, resulting in the higher permeation flux. And also, the equilibrium vapor pressure of the molecules will also increase as temperature increase, which gives larger driving force of the whole PV process. And also, this also contributes to the higher flux. So to sum up, basically the evaporation system for ethanol recycle from the TCM wastewater has been found to be technically feasible, and we have conducted a series of experiments to develop a possible design for the PV test. It was found that the optimal design is to conduct the PV test at 70 degrees Celsius, use 40 micron thick membranes, and which are prepared from the 30% PDMS solution. However, there are still some limitations in this research that can be further improved. For example, our self-made membranes can recover some ethanol indeed, but the selectivity is poor. This can be further optimized by applying multi-stage evaporation. And we also plan to purchase different types of commercial PV membranes to evaluate their performance in our system as well. And furthermore, we will add some bioactive compounds on TCM into the feed in the future work to better mimic real TCM wastewater.
I will finish.
And that's all for my presentation. Thank you for your
I will
time.
talk to them to join the.
Thank you very much
Actually, almost finished.
for the
Finished.
nice
Yeah,
presentation.
it's coming soon.
And since we needed
Okay.
to go to the
Okay.
closing ceremony quickly, so
All right.
if there's a quick question, I can
See you soon.
accept that.
Bye.
Or, otherwise, I will just have the conclusion on this session.
Yep. Okay.
Okay, I guess. Yeah, I guess there's no question.
So we can join the closing ceremony. Thank you, everybody, and we can see you soon, very soon, in the closing ceremony.
Yeah, thank you very much.
Thank you. Please click the closing ceremony in the event schedule. See you.
Hi, Sean.
Hello, Tao. How are you?
Hi, good. We are live now. We are live now. All the participants are in the room. So I think because you are inside the meeting room, I think we are ready to go.
Okay, thank you
Okay.
everyone. So I'm just going to start the recording, and once you hear the voice, please allow a few seconds and then you can start speaking. Thank you.
Thank you.
Recording in progress.
Good morning, good afternoon, everyone. Thank you for joining us for the closing ceremony. It was really hectic and busy days in the past few days. I hope you all enjoy the conference. It's a special event. We have never been have this event online. This time is really a special experiment. Like you are often trying in your lab. This closing ceremony will be held by me and by Professor Xiong and Professor Zhang, Yuebiao Zhang from Shanghai Tech. As we announced before, the main content of this closing ceremony is to thank the speakers and the selection committees, is to congratulate the young researcher best oral presentations and the student best oral presentations, as well as the student best poster presentations. The poster presentations will be starting first by Yuebiao, and then we'll go to Professor Xiong, and I will announce the young researcher best oral presentations. Yuebiao, please, you can take it over.
Thank you. So the student best poster presentation award is the third award goes to Jawad Mustafa. Congratulations. And the second one award go to the Yusik Kim. Congratulations. The first award goes to Hawaii Wong. Congratulations to all the awardees. They won the student best poster presentation. Thank you.
Thank you, Yuebiao. We will announce later how the student will get the money in their pocket. Let's go to the student best oral presentations. Sean, please.
Yes. So we have a lot of difficult time to select the candidature of the best oral presentation. So we have several third award because so many students presented very well. So first, we just say desalination editor award, student best oral presentation. So this third award goes to Lida Meng. His study is a study of membrane wetting mechanism in sodium chloride solution desalination process by membrane distillation. Big congratulations, Lida Meng. And second, the third award goes to Yang Mao. So super hydrophobic graphene-based membrane for membrane distillation desalination. Yeah, I chaired her presentation. Also, co-third award goes to Chen Wang. Inkjet printed high performance nanofiltration membrane for desalination. Congratulations, Chen Wang. Also, second award goes to Yu Ji Lim, fast water transport through biomimetic reverse osmosis membrane embedded with peptide attached pillar Arines water channels. Congratulations, Eugene Lim. The first award goes to Rong Her, the unprecedented magnesium lithium separation using layer by layer hollow fiber nanofiltration membrane. Big congratulations, Long Her.
Thank you, Sean.
Thank you very much.
So I will take it over for the Young Researcher Awards.
Yeah.
We had the same problem for selecting all the Young Researcher Awards because there are so many young researchers who just started their career. They have done a great job. They have a very excellent presentation. So we decided to expand a bit for the third award. We have 3 core third awards. So the first Dissemination Editor Award, Young Researcher Best Orientation, goes to Ralph Roddy Gonzalez for his second amino acyl amine modified thin film composite forward osmosis membrane for enhanced ammonium concentration and recovery. Congratulations, Ralph. The second core third award goes to Junbin Kim for his development of 1,000 cube per day seawater RO pilot plant in Abu Dhabi for low energy seawater desalination. Congratulations, Junbin. Our core third award goes to Dr. Junyong Zhu for his exploration of new methods to prepare polyamide-based nanofiltration membranes. Congratulations, Junyong. Now we are going to the second. Guess who is the second? The second award of Desalination Editor Awards Young Researcher Best Oral Presentation goes to Zhang Xin Wang for his comparison of energy consumption of osmotically assisted RO and low salt rejection RO for brine management. Congratulations, Zhang Xin, for your excellent work. Exciting moment. The Best Desalination Editor Award for Young Research Best Oral Presentation goes to Xi Chen for his excellent work on elucidating the roles of polyamide layer structural properties, impermeability, selectivity, trade-off. Thank you, Xi. Congratulations. For all the, if you want to get the money, or you can actively send emails to us, or we will get back to you. Thank you all for your presentations. Thank you all for your nice work. Congratulations all. Now we go to the next session. I will first have a couple words to everybody. I would like to thank all of you for strong support and participation to MEMDES 2021. Thank you for sharing your frontier knowledge and to other people. I'm sure many of us have learned a lot in the past few days. I wish everyone great success in your research and look forward to speaking to you in person in the next meeting. Yue Biao, do you have a few words to say to the audience?
Yes, I would like to thank all the attendees and speakers for their great contribution to this nice occasion. It was a pity we could not see each other in person, but I would like to invite you to visit Shanghai Tech in the future. Shanghai Tech University is a brand new university, and we have very nice facility and beautiful campus. So welcome to Shanghai Tech in the future. That's all.
Thank you.
Thank you.
Hello, Sean.
Thank you, everybody. So now it's time to celebrate our closing ceremony. Yeah, first of all, I'd like to thank you, Tao. Yeah, he has made extra ordinary effort and time to organize this successful conference. So 10th anniversary. Last year, we planned to have in-person conference every monthly meeting. We had a problem whether we will have online or hybrid or so many uncertainty, but Tao he made a very good progress, and then good leadership to organize the MEMDES. Now it's very much happy to see all the people, they benefit a lot, and very much appreciate. Also, Professor Yu Bia-Zhang, thank you for his support for all the infrastructure of the conference venue, and then we had a lot of meeting and discussion. Thank you for your follow-up and the teamwork. Also, we have a very strong support from the SBA. So Jessica and Mary Claire and Aaron, also Karen and Thomas. So many people involved, the professional support in terms of this online presentation as well as the physical related to conference preparation. So this online preparation has been prepared almost 2 weeks. So they are really extraordinary professional job have made to achieve this level of conference organization. I appreciate also their support. Also volunteer, Tao his sorry, Professor Wang from the Vice President of the Shanghai Advanced Research Institute, also his student. A lot of email communication, WeChat update, and I really appreciate his student and his secretary really contribute a lot for this conference. So I appreciate volunteer and Tao's staff. Also all the speakers, plenary speaker, keynote speaker, invite speaker, and then oral presentation speaker, poster speakers, also awardees. They are all great to make this successful conference. Thank you all, and then we will continue our networking and collaboration and engagement, and then we will see how we can interact each other for the future. And now it's a time to sit down and then write a paper. So Tao, can you go next slide? So special is ready, so you can submit your paper. Yeah, we can give you almost 2 paper for each presenter. So if you have any good quality of your manuscript in desalination, so please submit your manuscript by 30 June. I'm sure that Professor Tao and the other guest editors will try to improve your papers, as well as we can make sure that the citation of the reference, so last 2 years, 3 years, so you can cite the latest your references, and then we can also work on this desalination impact factor increase. So that's one of our collaborative activity we can do. Also, we have several special issues, not only MEMDES, we have membrane distillation special issue, COVID-19, and we have also osmosis assisted desalination, wastewater saline desalination. So if you go to the submission tab of the desalination, so you will see a lot of diversified desalination special issues. So please keep submitting your high quality manuscripts. We can help you to improve, and then we can publish together in the system. Okay, next, Tao. So this slide is from Xiwang Zhang and Professor Michael Duke. So they will organize the International Membrane Science and Technology Conference and in Melbourne next year, December. And if you are interested, please join this IMSTEC conference. And there are a lot of desalination related research topics and sessions, so you can enjoy also Melbourne and then Australian life there. And next, please. And thank you for your attention, and then we can see you in MEMDES 2023. So we will keep you informed where is the venue and then timing. Thank you very much. Tao and Yubiao.
Thank you, Sean, for your very much interesting and very much encouraging words. I would like to thank all the speakers, all the people who have done the work to the MEMDES. Hope you enjoy our meeting. Have enjoyed all the talks. So I'm going to close the session. I'm going to close the MEMDES 2021. Look forward to meet you in person in 2023. Thank you. Bye-bye.
Thank you.
Bye.
Good luck.
Good luck.
Well done, Tao. Hello? Hello, Tao? Can you hear me? Hello? Hello? Hello, Tao? Hello? 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 Hello, Tao. Thank you very much. Well done. Good job. And then, yeah. Thank you for your support. Now it's time to go for the hour. Yeah. So yeah, it's congratulations. So many things happened. I think so because yeah, we have managed well. Everything was very professional. Yeah. Absolutely, absolutely. Yes. Thank you. Absolutely, you did us very well. And now is we will work together for a long, long time. This is just the beginning of our journey. Right.
이런 거라고 볼 수 있습니다. 그래서 들어온 모든 에너지를 완전히 흡수하고 반사나 뭐 복사 이런 것들이 일어나지 않는 이런 물체가 가장 이상적이라고 볼 수 있는데 물론 이런 물질들을 만들어내는 건 굉장히 어려운 상황이고 어렵다고 볼 수 있고요. 그래서 흡수율을 높이고 반사율을 줄이고 복사율을 낮추는 이런 형태의 소재들을 찾고 있습니다. 그래서 1세대 이제 소재들을 보면은 이건 주로 이제 페인트 기반으로 한 그런 솔라 흡수체라고 얘기 드릴 수 있겠습니다. 예를 들면 뭐 블랙 카본이나 블랙 TiO2, 블랙 크롬, 뭐 그래핀 이런 것들을 이제 코팅을 한 거죠. 페인트 형태로 발라서 흡수체를 만드는 이런 형태고요. 이건 이제 광열 변환되는 효율이 떨어집니다. 또 이 내구성도 떨어지고 그래서 이것들을 개선하기 위해서 두 번째 이 세대에는 포러스한 멀티레이어 솔라 옵저버들이 사용이 되고 있습니다. 이거는 굉장히 높은 광 흡수율을 가지고 있고요. 맥시멈으로 보면 한 99%까지 에너지를 흡수할 수 있는 이런 특성을 가지고 있는 반면에 이건 이제 웨이브 랭스에 따라서 빛의 파장에 따라서 선택성이 없습니다. 그래서 보통 대부분의 에너지가 단파장 쪽에 있는데 이건 이제 그것들을 조절할 수 있는 선택성이 낮기 때문에 좀 비효율적으로 얘기할 수 있고요. 또 에너지를 트랜스퍼 하는데 조금 문제가 있습니다. 그래서 세 번째 이제 3세대의 태양열 흡수체는 이제 플라스모닉 현상을 이용하는 그런 흡수체고요. 저희가 뒤에 말씀드릴 부분도 플라스모닉 형태의 그런 흡수체에 대해서 말씀드릴 거고요. 요거는 굉장히 높은 광 흡수율을 가지고 있습니다. 또 이건 2세대하고 다르게 저희가 원하는 파장의 광들을 흡수할 수 있는 그런 파장 선택성도 가지고 있습니다. 근데 이건 이제 만들기가 조금 복잡하고요. 그다음에 가격이 좀 높은 이런 단점들이 있다고 얘기할 수가 있겠습니다. 그래서 저희가 이제 개발한 흡수체에 대해서 간단하게 말씀을 드리겠습니다. 이 흡수체는 저희가 사용한 흡수체는 이제 앞에서 말씀드렸듯이 플라스모닉 현상을 이용하기 위해서 그걸 통해서 이제 광의 흡수율을 굉장히 높게 가지고 갈 수 있고 파장의 선택성을 주기 위해서 저희가 타이타늄하고 그다음에 마그네슘 플로라이드를 이중으로 적층을 해서 사용하는 이런 흡수체를 저희가 저희 키스트의 방전 소재 연구팀하고 같이 개발해서 여기에 적용을 했습니다. 그림에서 보듯이 C 그림에서 보시면은 앱저번스 그러니까 흡수율은 굉장히 높고요. 또 다른 리플렉션이나 트랜스미션은 굉장히 낮은 이런 특성들을 가지고 있고요. 특히나 보시면 2 마이크로에서 4 마이크로 사이에서 굉장히 흡수율이 굉장히 높은 걸 보실 수 있습니다. 그리고 이제 리플렉션 같은 경우는 이제 4 마이크로 이상에서 높은 걸 보실 수가 있고요. 사실은 이 태양 에너지에서 2에서 4 마이크로 사이가 굉장히 중요한 에너지 파장대라고 보시면 되고요. 그래서 저희가 이걸 이제 어떻게 적층할 거며 몇 층으로 적층할 건지, 그다음에 두께는 어떻게 할 건지 이런 것들은 저희가 시뮬레이션을 통해서 옵티마이제이션을 했고요. 그래서 이제 저희가